Hello, good afternoon.
Good afternoon, sir.
Yeah. Okay, so can you see the OneNote?
Yes, sir.
Okay. So we are almost now end of the first chapter. Okay. Only two main topics are remaining. One is temperature dependent thermal conductivity and the contact resistance. Okay. So we stopped at this problem in the last class, which is a truncated cone of 300 mm height, okay, constructed of aluminium, and the cone has top surface heated to 540 degree, base is at 95 degree centigrade. Okay, and then we have the lateral surfaces of the cone are insulated. So we have to make 1D heat conduction assumption and calculate the rate of heat transfer from the top surface to the bottom surface. Okay. So we had I had a problem with the OneNote, right? So there was little difficulty to solve this one. So we start with the element, okay, area element here of dx thickness, and we calculate the radius at that point r, okay, which is a function of r1, r2, and distance x, okay. So we can write r radius at this point as r1 plus r2 minus r1 by l into x. So this factor r2 minus r1 by l as substituted as s, okay, and then I proceeded with the calculation of area of the heat transfer. Heat transfer area is pi r square, okay, and then using Fourier law of heat conduction, we can calculate the rate of heat transfer. We can apply this law, but the area of heat transfer is going to change in this case because it's a function of x. Okay, so we have to integrate by considering the change in the area. So when you integrate this equation, so you will get this simplify. You can apply the limits, okay, from top of the cone x equal to 0 to the base L. Temperature changes from T1 to T2. So apply the temperatures limits here and integrate from top to bottom. So when you integrate this function, you will get this as q is missing here. Okay, q into apply the limits from 0 to L. Okay. Apply the limits, and then you simplify this left hand side. Okay. So since we have minus sign here, so you can apply the lower limit first and then upper limit. Okay. So you will get 1 by r1, s is taken out. Okay, s is taken out, and then 1 by r1 minus 1 by r1 plus sl. On the right hand side, we have pi k t1 minus t2. So this can be, you can take the common denominator and then simplify this one. It will reduce to, plus r1 minus r1 will cancel out. Okay, so this way it simplifies. Then you can write the expression for q. Q equal to r1 square plus r1 sl divided by l. And substitute for s. We have that s equal to r2 minus r1 by l. So finally, this will simplify when you substitute for s to, okay, you can see that r1 squared and then your s into l. Okay, if you write s into l, it is nothing but s into l is nothing but r2 minus r1. Okay, r2 minus r1. So substitute there, and you have you can see that. Okay, again r1 square will cancel out, so you'll get only pi r1 r2 k t1 minus t2 by l. L is there. Okay. So this way we can simplify for the and get the rate of heat transfer Q as, okay. You can write this one pi R1 R2 as equivalent area. Okay. Then we have K thermal conductivity K T1 minus T2 by L. So this looks like a planar wall equation itself, okay, but area is not obtained as, what is this, pi R1 R2. So this is nothing but geometric mean area, geometric mean of top and bottom cross section. Truncated cone. Okay. So nothing but these are tops cross section area and the bottom area. So geometric mean of that. So if you look at the ellipse, okay, area of ellipse, so it will also have the same, okay, formula pi R1 R2, provided R1 is the minor axis, R2 is the major axis, or other way. But so that means if you have a elliptical cylinder, okay, if you have an elliptical cylinder of thickness, so length L, so we can say that the rate of, still we have that problem, sorry.
Screen sharing stopped.
Yeah, that's what. The OneNote is stopped. Okay, so this area is nothing but area of ellipse pi R1 R2. So we can say that 1D steady heat conduction through the frustum of cone or the truncated cone is equivalent to conduction through elliptical cylinder of minor radius R1, major radius R2. Okay, right. So we can now substitute and obtain the rate of heat transfer. Okay, we have the formula Q equal to pi R1 R2 into K T1 minus T2 by L. So pi into R1 is 0.0375 R2. Then thermal conductivity of aluminum 205 into 540 minus temperature, base temperature is 95. So I think substitute 90 there. Okay, 95.
Sir, but this question has a circular cross section, right? Not oval, right?
Yes, not oval, circular cross section. Okay. Yeah.
So why are we getting pi R1, R2? This is for, are you solving it separately? Like if it was an elliptical cylinder?
No, it's just if it is a elliptical cylinder of same length, okay, then rate of heat transfer is same as, okay, the frustum of cone also. Both are same. Both will give same rate of heat transfer. So this value is much 22. I think this is 95. So this will be little less than that. Okay. So what is the actual value?
So in the last class, we didn't use it. We didn't solve it using this elliptical cylinder, right? So
No, it is exactly same process. Okay, everything you did. Okay, it's the same. So only thing is, today I gave you the final form. This one reduced equation. So I was struck, right, because of the one note. I was struck somewhere here, but you told me the answer anyway. Okay.
Yes, sir. So why are we
Now,
replacing that S with in terms of R2, R1 when we can already solve it using S?
yeah, okay, you got additional information here, right? It's like a simplify whenever you get a problem of similar nature. Okay, you don't have to go and integrate from the beginning. Okay, you can simply remember, yeah, simply remember this equivalent area, and you can do the problem. Right?
Yes, sir.
Okay. So then we move on to the next topic, that is.
So
Yeah.
I had a note in question 12.
Ah,
We didn't actually solve the second part of the question. I think we missed that.
second part, you mean we have to calculate only rate of heat transfer, right? What else?
So question 12.
Question number 12. Okay. Just a moment. Question number 12. So what was the second part there? Insulation. Electrical insulation.
Thickness
This cable of
that
5
allows
mm
maximum
outside
heat.
diameter, right? So we have to calculate, find the relative thickness of the rubber, which keeps the heat transfer same as if it were bare cable.
Yes,
That is
sir.
the, yeah.
Thickness for maximum heat transfer.
Okay. That is simply substitute formula of critical thickness. Okay.
Yes, sir.
So can you tell the answer of that question?
Critical thickness will come out to be 5.136. Sorry, not this one. This is the thickness. Critical thickness is 3.5 mm. Correct? K by H.
Yes, sir.
Yeah, and the thickness of the insulation which is having same heat transfer as the bare wire is 5.136 millimeter. 5.136 millimeter. Not thickness, radius, sorry. Radius of the insulation R2 is 5.136 millimeter. So thickness will be, then you have to calculate, you have to subtract the radius of the wire. Okay, you'll get the thickness.
So it's the 3.5 minus 2.5.
No, that is critical thickness. Okay, but if you want the thickness which is allowing same heat transfer as the bare wire, then it is 5.136 minus 2.5.
Yes, and for the maximum heat transfer, it is RC minus radius.
Yeah, yes, exactly.
Yes, okay.
Okay. Okay, shall we start? This temperature dependent thermal conductivity, and you can see the chart here, which shows the thermal conductivity variation for different materials with respect to temperature. Okay, so only few materials that show a strong dependence of temperature dependent thermal conductivity, like aluminum oxide. You can see that. So the thermal conductivity varies very much. Also, the stainless steel shows the increase in thermal conductivity. Quartz also shows very strong dependence on thermal conductivity, temperature. Okay, but most of the metals here, you can see that they have a almost horizontal line. But okay, so what is this one is, we have done the problems where we assumed thermal conductivity as a constant value. irrespective of what is the surface temperature or temperature of the wall. We have taken a single value. Okay. Now what we have to do is we have to see what is the temperature at particular location of the wall and calculate the thermal conductivity at that temperature and use that in the equation. Okay. But what do you think about this variation of thermal conductivity with the temperature? Is it linear or non-linear?
Polynomial variation.
Yeah, most of them are non-linear. Okay, you can approximate it. Okay, for example, if I take stainless steel, okay, it is almost a line, right? Variation is almost a straight line. Okay, so but the problem here again is you cannot clearly tell because it's a log gap. This one graph. Okay, so that is the problem. But if we have a small range of temperature, then we can make the approximation. Small range mean, for example, if I have a copper wall of thickness 5 mm and the temperature varies from one side to other side is maybe 50, maximum temperature difference is 50 degrees centigrade. Then in that 50 degrees centigrade, the variation in thermal conductivity can be taken as a linear variation. Okay. So generally, how we relate this temperature dependent thermal conductivity is using the thermal conductivity at 0 degrees centigrade. Okay, K0 is thermal conductivity at 0 degree centigrade into 1 plus beta. Here beta is temperature coefficient of thermal conductivity. So by looking at this equation, can you tell me what is the unit of beta? So what is the unit of the thermal
Inverse
conductivity?
of temperature.
Yes.
Inverse of temperature.
Okay, inverse of
Degree.
temperature. Yes, exactly. So watts per meter degree centigrade is the unit. So K naught as that unit. So beta into T should not have any unit. Okay, beta into T should not have any unit. So beta is having the unit of 1 by degree centigrade. 1 by degree. So we can use this linearizes the equation only for limited range, okay, not for entire temperatures range. So when we have a limited temperature range, we can find out the beta value for that range and we can use this formula, which is, but generally if you look in the internet or some data and book, we will get this polynomial, higher degree polynomial relation with relation of thermal conductivity with the temperature. Okay. Simply, if I want to tell you this, K can be written as A0 plus A1 into T plus A2 into T squared plus A3 into T cube, like this. Okay, this is a higher order polynomial. So A0, A1, A2, A3 will be are the constants. Okay, that depends on the material. So this is highly nonlinear variation of this can capture that highly nonlinear variation of thermal conductivity with the temperature. Okay, but this is a linear relationship. The first one. So in this course, we are not going to use this type of nonlinear correlations. Only the linear variation of temperature dependent thermal conductivity is considered. So straight away we will take a planar wall and we will see how to estimate the rate of heat transfer when the thermal conductivity is given as a function of temperature. K equal to K0 into 1 plus beta T. Okay. So the problem here is derive an expression for temperature distribution in the slab under steady state condition. Okay. We have to obtain the temperature distribution in a wall of thickness L, where the thermal conductivity here is not constant, but the function of temperature. K is function of temperature, K0 plus 1 plus beta T. Okay, one more important thing is you have to observe that some materials show increase in thermal conductivity with temperature. So look at the graph and can you identify some materials which show that increase in thermal conductivity?
Tungsten. Tungsten. Sir.
Yeah.
So fused quartz.
Fused quartz.
Quartz. Okay. Fused quartz.
Tungsten.
Then stainless steel.
Stainless steel.
Right. Yes. They show that increase in thermal conductivity, and also platinum. You can say for higher temperatures. Okay. It shows a increase in thermal conductivity. So remaining these metals like copper, silver, aluminium, all these show a same trend. I can say the slope is not so high, but there is a decrease in thermal conductivity with increase in temperature. So how to write where that parameter will go? So depending on the beta value, we can say that the thermal conductivity is increasing or decreasing. Okay. So if beta is positive, right? What is the meaning of that? If beta is greater than 0,
increasing trend.
Yeah. So stainless steel and fused quartz, they have the beta value, okay, greater than positive value, greater than 0. Yes.
Given this trend, there must be an optimum service temperature for every material, right? Because at one temperature, it might be pointless to use aluminum oxide, whereas it may make more sense to use stainless steel.
Okay, that is exactly what the material science people have to know, do it. Okay, also it transfer. Like when you select the material, we have to see the temperature range, and based on that, we have to select. Okay, so definitely same material cannot be applicable for all temperature range. Okay.
Yes, sir.
So yeah, here the positive trend means beta is positive. Okay, that means thermal conductivity increases with the temperature. If beta is negative, then thermal conductivity decreases with the temperature. Now, if you have a left side surface at T1 and right side surfaces at T2, definitely we can see that T1 is greater than T2 in this case. Okay, T1 is greater than T2, and I will ask some question, one question here. So if beta is greater than 0, that is beta is positive, then okay, tell me where the thermal conductivity value is more, whether on the left side or right side. For beta greater than 0,
Left side.
okay,
Left side, sir.
so thermal conductivity is more on the left side. Okay, clearly you can see that because temperature is more means beta into T, that will be T value is large. So this 1 plus beta T will be the large value at the left surface compared to the right surface. So K, I will write it as left surface is greater than K right surface. Okay. But if beta is less than 0, for example, metals, right? Copper, aluminum, and all. What you see is beta less than 0. In that case, what do you expect? K on the left surface is less than K on the right side. Okay. So now you can see that there are three curves. Okay, for positive beta, beta equal to 0, and beta equal to beta less than 0. So you have three trends, different. Okay, when beta is 0, what will happen is there is no dependence on temperature. So we have K equal to K0. That is what we did for last 5, 6 class. Okay, where we assumed the thermal conductivity is constant. Okay, so we have a straight line variation of temperature. Okay, temperature profile is a straight line for beta equal to 0. Now, when beta is greater than 0, what will happen? How the profile changes. So left surface thermal conductivity is more compared to the right surface. That means you can see that the slope is less here, right? This was discussed in the first class itself, I think. You have a wall, and if the temperature profile is okay, almost horizontal, that means the thermal conductivity is large. Okay, but if there is a large temperature drop across the wall, that means it is having low thermal conductivity. So you can understand here. So the slope is less here compared to slope is more on the right side. That means, okay, this is for beta greater than 0, we will get this nature of the curve. Okay, nonlinear variation of temperature within the wall. And it is vice versa for the other case. When beta is less than 0, we have high thermal conductivity at the right wall. So it is almost horizontal here, but slope is more at the left wall. Okay. So understand this. Okay, it's not so difficult. Now we can obtain the expression for temperature distribution in the slab. Okay. So for that we use the same Fourier law of heat conduction. So you consider an element of in the wall of thickness dx, and we can write Q equal to minus Ka dt by dx. Okay. Then substitute for K. Q equal to minus K is nothing but now K0 into K0 into 1 plus beta T into A dt dx. Okay. Now we have to integrate as we did before. That's all. Only thing is we have to consider this 1 plus beta T when we integrate dt. So I can integrate integral dx k naught a integral 1 plus beta T dt. Okay, you can apply the limits from x equal to 0 to L, and the temperature varies from T1 to T2. Okay. Or first, okay, we have to calculate temperature distribution. So let's just integrate indefinite integral. So then we can write this as Q into x minus K0 A. Okay, come on, integrate this function 1 plus beta T into dt. T plus beta T squared by 2. Then integration constant. Okay. So any problem here? No, right? Tell me, you are following it or not?
Yes, sir.
Yeah, just we have the problem with the thermal conductivity. Okay, that is the not a constant value, but it's a function of temperature. That's all. So when you integrate, you will get this function. Now apply the boundary conditions. We know at x equal to 0. Okay, we can obtain that constant c. Come on, tell me what is the constant c? C equal to K0 A into T1 plus beta T1 squared by, okay. Now substitute into this form, okay, equation, and you have the expression for temperature distribution. So I will write C first, okay, K0 A into T1 plus beta T1 squared by 2 C, then minus K0 A into T plus beta T squared by, okay. Now we can simplify further, and we can write this as K0 A can be, we can bring it to the left hand side, Qx divided by K0 A. On the right hand side we have T1, so right, T1
N.
minus E, yes, and then beta by 2 into T1 square minus T square. Okay, so this is a equation of temperature distribution, or if you want, you can simply write other way also, beta by 2 into T1 squared minus T1, T squared plus, okay, T1 minus T2, T, sorry, then minus Qx divided by K0 equal to, so this is the temperature profile. Okay. So what is this profile is? Is it a linear?
Quadratic.
Quadratic profile. Okay, it's a quadratic. Next, we can also estimate the rate of heat transfer. We have to integrate from left surface to the right surface. So apply the limits, and we can estimate the rate of heat transfer. Q integral from 0 to L, thickness of the wall, dx. On the right hand side, we have minus K0A integral from temperature T1 to T2, and this is 1 plus beta T dt. Okay. So when you integrate this and apply the limits, you will get Q into L there minus K0A, and here we get T plus beta T squared by 2. Apply the limits from T1 to T2. Okay. Otherwise, since minus sign is there, so you can take that minus sign and change the limits. Okay, interchange it. So that also you can do. So now apply the limits, and you can write this as minus K0 A T2 plus beta by 2 T2 squared minus T1 minus beta by 2 T1 squared. Okay. Or you can do another thing here is take the minus sign inside. So A K naught into T1 minus T2, then beta by 2 into T1 squared minus T2 squared. So T1 squared minus T2 squared can be written as T1 squared minus T2 squared can be written as T1 plus T2 into T1 minus T2. So you can take out that factor T1 minus T2 and you can write this as A into K0 into T1 minus T2 taken out. So 1 plus what we have beta by 2 into T1 plus T2. T1 plus T2. Okay, now tell me what is this T1 plus T2 by 2. This is nothing but arithmetic mean of the surface temperatures, left surface and right side surface temperatures. So simplify this one to write AK0 T1 minus T2 into 1 plus beta into T mean. Is it okay? So we can take the, if you know the surface temperature, left surface and right surface, then we can take the average value, that is mean value, and we can substitute here. And further, we can write K0 into, let K mean equal to K0 into 1 plus beta into T mean. Okay. Now what you can see that if I substitute for K mean, okay, then I will have this as Q equal to, or L is there, Q into L is there. So Q equal to A K mean into T1 minus T2 divided by L. Or simply, you can write in the same format which we wrote for the planar wall with the constant value. But here the K value should be evaluated at the mean temperature. That's all. So we can write this as T1 minus T2 divided by L by A K mean, which is nothing but the thermal resistance of the wall. So simply remember that the formula remains same. Only thing is thermal conductivity K should be evaluated at the mean temperature. K mean equal to K0 plus 1 plus beta into T mean. And T mean is given by T1 plus T2 by 2. Okay. So this will work for only the linear profile. Okay, linear profile it will come like this, but if it is non-linear profile, we are assuming, then we cannot simplify to this level. Okay. So, but in the course we are usually considering the linear profile, so it's an advantage for it. Okay. So any doubt here?
Sir, can you scroll up?
Up. Okay. Yeah.
It's a little more.
Still more. Okay.
Yeah,
Yeah.
here. I forgot to copy this time. I couldn't copy.
Okay. Right on. No problem. Okay, so this can be done for planar, cylindrical and spherical walls. Okay, same process can be repeated. So the only thing is you have to substitute for thermal conductivity as a function of temperature and integrate them.
Yes, sir. Done.
Okay. Okay, for cylindrical wall, again the same thing. We consider the Fourier, we apply the Fourier law. Okay, remember the area is going to change in the cylindrical and spherical wall. So always that should come to your mind. Okay. So rate the heat transfer area you write down first for any element at radius r. Heat transfer area is nothing but 2 pi r l. Okay. And thermal conductivity. Okay. So this, okay, here it is beta or alpha or any other notation is used. Don't confuse with that. Okay, it simply mean that it is a temperature dependent thermal coefficient of thermal conductivity. Okay, beta or alpha or sometimes gamma is used. Don't worry about that. Okay. So if you want, I can use the notation K equal to K0 into 1 plus alpha T. Okay. Alpha into T. Or sometimes it can be written as A plus BT. What is the meaning of here? A is nothing but K0 and B is nothing but alpha into K0. Okay. So the values will be given A, B or alpha K0. Okay. These values will be given to you. Then it is safe. Okay. If you want A plus BT, I can use. So this we already done, right? K0, K equal to K0 into 1 plus beta T we have done. So let me use K equal to A plus BT. So now apply the using Fourier law for Q equal to minus K A dt by dr. Okay, radial heat flow in this case, radial direction, r direction. Substitute for area and thermal conductivity. So you can write this as minus K is nothing but A plus BT. Area is 2 pi r L and then dt dr. Separate the variables. Okay, r dr should come to the left hand side. So I write Q into integral dr by r equal to minus 2 pi L. Okay, then integral A plus BT dt. Check it. Anything missing? 2 pi r, 2 pi L is here. R is taken to the left hand side here, and then okay, everything is okay. So limits, we can integrate from inner radius R1 to outer radius R2. And the temperature at the inner radius is T1, temperature at the outer radius, okay, T2. So same thing, you did it before. We get this as ln r. Apply the limits R1 to R2 minus 2 pi L here when you integrate, you will get AT plus BT squared by 2. Apply the limits T1 to T2. Okay. What you get is here Q ln R2 by R1. On the right hand side, we have minus sign, so I can apply T1 first and then T2. So 2 pi L A into T1 minus T2, then B by 2 into T1 squared minus T2 squared. So what you see on the right hand side within this square bracket is almost same as before. Okay, we have T1 square minus T2 square, which we can write as T1 plus T2 into T1 minus T2. And that factor T1 minus T2 is here also, so we can take it out. And this can be written as 2 pi L T1 minus T2. And in the bracket, we have A plus B into T1 plus T2 by 2. Again, it is a arithmetic mean of inner surface temperature and outer surface temperature of the cylinder. Okay. Simply, we can write 2 pi L T1 minus T2 into A plus B into T mean. Well, wait a minute. I think we made a mistake here, right? No. Okay, correct. So A plus BT is nothing but, so we can write this as K mean equal to A plus B T. Then Q is given by ln, T1 minus T2 divided by ln R2 by R1 divided by 2 pi Lk. Or I can write here itself 2 pi L T1 minus T2, and then this is K mean. K mean. Okay. So there is no change in the formula. Only thing is the thermal conductivity value has to be found out by using inner and outer surface temperature. Okay, mean value. Okay, substituting that mean value, we know the thermal conductivity to be used. For spherical case, you do it. Okay. The process is everything is same. Integration, we have done it earlier. So then it will simplify to the same formula. Okay. So tell me, what is the formula for spherical case? It will come out to be Q equal to T1 minus T2.
R1.
Yeah. R2 minus R1 divided by 4 pi. Okay. R1 R2
K mean.
K mean. Okay, that's all. And K mean is given by the whichever formula you use. Okay, depending on that. If you're using A plus B T, K equal to A plus B T, then it will okay, it will be same format. Okay. Or if you are using 1 plus K0 plus K0 into 1 plus beta T, then A plus B T mean. It depends. Okay. But formula will not change. Okay. So we'll take up few problems now. So in this problem, we have a non-linear profile. Okay. Problem number 16. A brick wall of 300 mm thick, having a thermal conductivity K equal to 1.007 plus 0.001 T square, as its surface temperatures 100 and 28 degrees centigrade. Find the rate of heat transfer through 5 meter square area of the wall. Okay, area is given. So thickness of the wall is given, which is 300 mm, and the thermal conductivity K is 1.007 plus 0.001 T squared. Okay, so it varies with the temperature, square of the temperature. And area of the wall is given, temperature on the two surfaces is given. T1 is given and T2 is 28 degrees centigrade. Here the temperature is 100 degrees centigrade. Area is 5 meters square. So what do we have to do? We don't have the formula for this type of profile, but if it is given as the instead of T square, if it was T, then we had the formula directly. We can use that formula and do the problem. Right? If it is 1.007 plus 0.001 into T, okay, then we can directly apply that formula. But we have T square there, so that is why we have to integrate and do it. So using Fourier law. So again, you have to do that. Basically, you have to consider a element here. Okay, vertical element, and then that is at distance x from the left side. And then for this element, we are applying this Fourier law. So Q equal to minus K A dt by dx. Substitute for K minus 1.007 plus 0.001 T squared. Area is 5 into dt by dx. Integrate from left side to the right side. So Q integrate from 0 to 0.3 dx minus 5 integral 1.007 plus 0.001 T square dt from temperatures 100 to, or you write T1, T2, then we'll come back to T1, T2. Okay. So if it, on the left hand side, we get it as 0.3 Q equal to minus 5. What you get here is 1.007 T plus 0.001 T cube divided by 3. Apply the limits T1 to T2. Okay. So minus sign is there. So I'll take that minus sign inside and I'll write this as 1.007 into T1 minus T2. Then this as 0.001 into divided by 3 into T1 cube minus T2 cube. Okay, that's all. So simply you should know how to integrate, that's all. T1 is equal to 100, T2 equal to 28. So Q equal to 5 divided by 0.3 into 1.007, 100 minus 28, then 0.001 divided by 3 into 100 cube minus 28 cube. So what is the value?
6.64.
26 or 6?
6.6.
Okay, 6.62 kilowatts.
6.642 kilowatts.
Okay, 642. Or that is 6,642 kilowatts. Sorry, not kilowatts, watts. Okay. It's a very simple problem. If the profile is given and the temperatures are given, surface temperatures are known means it's not a problem at all, right? So what you understood from the derivations is thermal conductivity or temperature dependent thermal conductivity will problems will simplify. Okay, if you know the surface temperatures. But the next problem we have, yeah.
Can you scroll up one time just near the Fourier law?
Okay, sure.
Just
Which one?
Yeah, sir. Yeah, only just 1 minute. Yes, sir. Done, sir. Thank you, sir.
Okay. Yeah, that's what I was telling, that if you know the surface temperatures, right side and left side surface temperatures, then if the profile is linear, or temperature dependent thermal conductivity is assumed as a linear with relationship with the temperature, then we don't have any problem because we have to substitute only K mean in the formula and do the problem. But if you have a problem where you don't know the surface temperatures, okay, then the problems becomes complex. So next problem what we have is of that nature. So brick work of a furnace is built up of a layer of fire clay. Okay, this is the fire clay wall where whose thermal conductivity is a function of temperature. K0 and beta values are given here. The brickwork is 250 millimeter thick. Determine the loss of heat from 1 meter square of the brick surface and the wall surface temperature if the temperature of the gas is 1200 degrees centigrade and the room temperature is 30 degrees centigrade. So we have a furnace. One side of the furnace there is hot gas which is having temperature of 1200 degrees centigrade. But outside in the room temperature is 30 degrees centigrade. Assume the surface heat transfer coefficient for the inside surface or the furnace side, okay? Inside of the furnace, that is 30 watt per meter square Kelvin, and the outside surface is 10 watt per meter square Kelvin. So we don't have the temperatures T1 and T2. Okay, that is the problem we have. We know T1 and T2 we can estimate the rate of heat transfer very easily. Just take the average of T1 and T2, substitute into the formula and obtain K mean and use the same formula which we used previously. But in this case, we don't have that liberty. So we have to do solve the simultaneous equations to obtain the temperatures here. So what is we can see that there are three resistances. So on the left hand side we have a convection resistance RH1, then conduction resistance RK, and then convection resistance on the right wall outside here, right? So you can write the rate of heat transfer by convection. So this is Q convection, and let me write this as 1. Then through the wall Q conduction, and from the wall to the outside again Q convection 2. So at steady state, Q convection 1 equal to Q conduction through the wall equal to Q convection 2. Okay. Now write the formula for each this one. What is Q convection 1? Estimate that. Again, remember that area of the wall to be considered is 1. Okay, area of
HA delta T.
Yeah, HA delta T. Okay, 1 meter square area. So then you can substitute for that first only. Q convection 1 equal to H F1, I think, or H1 should be. H1A delta T here. Delta T is TF1 minus T1. So what is H1? H1 here on the odd side, that is 30 watt per meter squared Kelvin. On the cold outside, we have H2 equal to 10 watt per meter squared Kelvin. So then H1 is 30, area is 1, and delta T is TF1 minus T1. Right? Okay, can you write now Q conduction? This is Q convection in 1. I'll write. What is Q conduction? Through the wall. So thickness of the wall you can take instead of X. If you're confused, you can use L only, no problem. Okay. So what is Q conduction? What is the formula? We can write T1 minus T2.
K mean.
Right? Yeah. Or we don't need to write in the resistance form. We'll write this. K mean into area. Okay. Into temperature difference T1 minus T2 divided by thickness of the wall L. So wall thickness is given, that is 250 millimeter. Okay, brickwork is 250 millimeter thick. L equal to 0.25. So area is known. Okay, so we can write this as 1 divided by 0.25 K mean into T1 minus T2. I'll write first. What is K mean? Come on, K0 into 1 plus beta into P mean. That is the formula given here. Okay, K0 plus 1 plus beta T. So K mean equal to. So you can substitute for that. K mean I have to write here. That is K0 into 1 plus. Yeah. let's substitute everything together. So I'll just remove that 0.25 and keep L itself. K0, 1 into 1 plus beta into T mean. Okay. T mean is nothing but T1 plus T2 by 2. So Q conduction can be written as K0. Area is 1, so it's divided by L into T1 minus T2 into 1 plus beta into T mean. You can replace now T mean as T1 plus T2 by 2. Is it okay? So T1. So further, if you want, you can simplify this one. And you can write it as K0 by L there into T1 minus T2. Then K0 beta divided by 2L into, what is this? T1 square minus T2 square. Okay. So we can see that K0 is known, L is known. Here also we know K0 beta L. So, but only we don't know T1 and T2. Okay, next. Let's say this is 1, convection 1, this is 2. Okay. Next, Q convection 2. On the right wall, there is H2, A, delta T. H2 is 10, area is 1, delta T is T2 minus TF2. Okay. TF2. So this is 3. Okay, now we have written convection is same as conduction, same as convection 2. So we can make the equations using that relationship and obtain T1 and T2. Then we can obtain the rate of heat transfer. So TF1 is known. I'll write that equations again. Q convection 1 is 30 times TF1 is 1200 minus T1. So what is this value? 36,000 minus 30 T1. Okay. Next, this third equation also we can write same way. Equal to 10 T2 minus TF2. What is the value? Temperature on the other side is 30 degrees centigrade. So 10 into 30, that is 300. 4. And 5. Okay, now you can write from 4 and 5. Okay, you can write one equation, right? So you can say that 36,000 minus 30 T1 equal to 10 T2 minus 300. So you can replace T1 with respect to T2 or T2 as a function of. So everywhere you can see that here 10 is the minimum value. If I divide by 10, I can remove 1 0 there everywhere. And I can write an equation for T2 equal to Tell me. So this is 3600 minus 30 will come this side, means plus 30. So we have 3630 minus 3t1. So this is one of the main equations I want to solve. Now you can equate conduction with convection, one of them, any one you can choose, no problem. Okay, so if I equate convection 1 with conduction from 3 and 4, 3, oh sorry, not 2 and 4, not 3, 2 and 4. 2 is conduction equation here we have. So what you can say, K0 by L, K0 by L into T1 minus T2 right? You can, yeah, you can, yeah, let it be. So if you want to simplify, save the time of writing, then you can put this K0 by L as some factor or some variable, okay? PQ something, P, and this as a Q. So you can write that way also. Only it's so from 2 and 3, 2 and 4, you can write P into T1 minus T2 plus Q into T1 square minus T2 square, T1 squared minus T2 squared. From 4, we have 36,000 minus 30 T1. Okay, so this is another equation we have. So further, we can separate out T terms, T1 and T2 terms. So P into T1. Oh. Tell me, we have P into T1 and here minus 30 into T1, right? So I can write 30 plus P into T1. Okay, then we have Q into T1 square, Q into T1 square minus P into T2 minus Q into T2 square. On the right hand side, we have 36,000. Now substitute for T2. T2 we can substitute in terms of T1. Okay. So 30 plus P T1 plus Q into T1 squared minus P into T2 can be written as, okay, you can write here, substitute 2 into 4 T2 from equation, okay, Roman 1 to from 1. So T2 can be written as 3630 minus 3T1. Okay. Now we have squaring. Okay, square of 3630 minus 3T1 whole square into equal to 36 1000 on the right. So simplification should be systematic, otherwise most of you will make mistake here. So 30 plus P, and from here how much you will get again? Minus will become plus. So you will get 30 plus P, then again plus 3P into T1. Okay. Then we have Q into, come on, T1 square is there. So then we can take P into 3630 to the right hand side because it's a constant. So we'll leave it there. Expand this one. Expand minus Q into, come on, expand this one. We have 3630 squared plus 3T1 squared, 2 squared. Again, yeah, minus, okay, minus 2 times 3630 into 3T1. On the right hand side, we have 36000, and we left something here, so that is plus 3630 P. Okay, now simplify to collect all the terms. We have 30 plus 4P, P plus 3P, and what else we have from here? 2 into 3630 into 3. How much is that? 2 into 3630 into 3. How much is that? Come on. 3630 into 2 into 3. How much? Rajat or are you there? Rajat.
Yes, sir.
Yeah. What is that value? 2 into 3630. No, not that one. 2 into 3630 into 3. This value.
21780.
I want to combine T1 first. Okay. 21,000.
21,780.
780. Okay. So this is 21,000. 21,780. 780 cube. Okay. So here you can see that this is minus sign. This is minus, so it will be plus. Into T1. I could have wrote down. So that is 30 plus 4P plus 21780 Q into T1. Next, T1 square. Okay, we can collect T1 square. One is Q here, then minus 9 Q T1 square, right? And on the right hand side, 36000 plus 3630 P, and what else we'll get from here is 3630 squared cube. Okay, tell me if any mistake is happened now only. Any mistake?
No, sir.
No, right? Okay. Now you can substitute for P and Q. Okay. So and tell me what is the equation. So only thing is you'll get a quadratic equation and then solve it for T1. So P is nothing but K naught by L. So K naught is given as 0.84, L equal to 0.25. 0.84 divided by 0.25. So this is almost 3.36. And Q is K naught beta divided by 2L. K naught is 0.84. Beta is how much? Okay, very small value, 0.695 into 10 power minus 3. 0.695 into 10 to the power minus 3 divided by 2 into 0.25. Okay. So this value will come out to be 1.1676 into 10 to the power minus 3. So that is why I put it as a Q, P and Q, because if you write those values, okay, initially itself, then there will be a lot of trouble to simplify. Okay, every time you have to write this small value, means you know how much inconvenience it is. Now substitute here and simplify, and what tell me the factor with the t and t1 squared. So what is the factor we get? Or first you can write t1 squared, that is 8q minus 8q t1 squared, then 30 plus 4p plus 21780q into t1 minus this entire 36000 plus 3630 p then 3630 squared into q equal to 0. This is the quadratic equation. Okay. Tell me what is 8 minus 8q equal to?
Minus 0.013.
Minus 0.013. Is it minus? Oh no. 8 into 1.1676. That is 9.34.
Into 10 to the
Yeah,
power minus
9.34 into 10 to the power minus 3, right? Okay. 9 point. So we will get minus 9.34 into 10 to the power minus 3 t1 squared. Okay, next, this value will be a large value. Oh, no, okay, again 4 times p plus 30, and this calculate 30 plus 4 times 3.36 plus 2178 into
68.87.
68.87. 68.87 T1, and this is a very large value. Okay, 63.
63582.17.
Yeah, 63,582. 0.14. So if you get this equation, that is done. Okay, you will get maximum points. If you make any mistake up to this point, then you will lose the points. Now, obtaining solution to this quadratic equation.
108.
Okay, you can use your calculator. Yes, T1 equal to
1008.
108.
1082 degree centigrade. That's all. So once you know T1, you know how to calculate T2. Okay, T2, we have the relation here. T2 equal to 3630 minus 3 T1. 3630 minus 3 times 1082. So what is the value?
384.
84 degree.
384, sir.
Sorry, 384, right? 384 degree. So now you can calculate T mean and also calculate the rate of heat transfer. Or you can just use the convection. So rate of heat transfer. Any formula you can use, no problem. Okay, Q equal to H1 into TF1 minus T1. H1 is 30, TF1 is 1200 minus 1082. So how much will be?
3539.82.
Okay, 25
3539.
3539.82. Okay, so this is how we can. Okay, one more thing is you have to do the cross verification. Okay, if you have done some mistake, you can do that cross verification because you have other convection outside. You can estimate there also, or you can use the conduction formula. So if you use conduction, then first calculate T mean. 1082 plus 384 divided by 2. So you'll get 733. Okay. Now we can calculate K mean. Right? K mean equal to 1 plus K0 is 0.884 into 1 plus beta is 6.695 into 10 to the power minus 3 into T mean, that is 733.
One point 268.
1 point, okay, 268. So you got 1.268 watt per meter Kelvin. Meter degrees. So we have K mean. Now we can calculate Q. Conduction area is 1, so you can write this as T1 or K mean into T1. Yeah, T1 minus T2 divided by
all the heat
L.
transfer rates are equal, right?
Yeah, it should be equal. No, this is for verification. Okay, just check it. 1.268 into 1082 minus 384 divided by L 0.25. How much you got? 35. Right.
3540.
Okay. So that is exactly same there. So okay. So this type of problems, okay, you have to be very careful. Most of the times when the wall temperature is not given or interface temperature is not given by like you have two walls where the thermal conductivity is function of temperature, then the problem will be a quadratic equation and then you have to solve that equation. Okay. So if the surface temperatures are given, then it's very simple. So practice similar problems, 1 or 2, so that you can answer. So you can see that this problem is a really good problem, okay, and takes time to solve this. So other thing I want tell you about this cone problem, right? So there you can expect other type of problems, okay. Maybe we can take square pyramid or frustum of pyramid, okay, square pyramid, right? Then you should know how to do that. So again, the process is same. You have to find out the heat transfer area, okay. In case of square pyramid, what will happen? What is the area? Square area is square of the length, side length, okay. So that we have to consider. So it is almost similar. You will get a similar expression there also. Okay. Try to do it. Do that problem also. Consider same side length for the bottom, top, temperature also same, and do the problem for a square pyramid. Okay. Frustum of square pyramid and
There will be a logarithmic term in it.
yes. No, this is a. Can you repeat me? Srinivas, right?
I think
Yeah.
there will be a logarithmic term in it in the square pyramid.
No. It will not come because why you think it will come logarithmic term?
Something I remember is from first year.
No, because I think again it will be square of the side length. Okay, so we have a square there, so it will not come. But if it is tapered fin, okay, that time it will come. Okay, so it is only one directional. So remember that your square is there, right? Area in the area R square is coming, so that's why there is no logarithmic term. But if it is only function of side length, not the square of the side length, then definitely you will get a logarithmic function. Okay, check it. So any doubts in today's class? Yeah. No doubts, right? Tell me if you have any doubts, any problem. Okay, we can discuss it now. So, and last class, I think there was a doubt in question number 2. Who raised that? Nachiketa? Yeah, hello. Tell me, Rajat, you got that right? Question number 2. I gave one formula to calculate rate of heat transfer there. Rajat. Yeah. So did you cross check that? I think we did. What I did there is the first calculation. After the first calculation, the rate of heat transfer there through the third wall will come as 8.08 kilowatts, not 8.8 watts kilowatts. Okay.
8.08 only, sir.
Yeah, 8.08 it will come, and using that formula, it will come around 8.07 kilowatts. Okay, and that little difference is because we are neglecting the decimal values when we estimate the resistance. because of that, some loss of this accuracy will take. Because of that, we are getting a little more value, 8.08, and one side we are getting 8.07. That's all. Okay, both values will come same. You can check it again. Okay, so that's all. Today I will stop here. I will not start that other part. So one small portion is remaining. So then we will start the rate of it. Uniform heat generation chapter next class. Okay, Thursday. Yeah. Srinivas, any questions?
Thank you, sir.
No. Yeah. Any questions? Tell me.
No, sir.
No. Okay. I'll stop now. Okay. See you on Thursday.
Thank you, sir.
Thank you, sir.
Okay. Yeah.
Thank you, sir.